Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody from the future. So I think it's on mute here. Now you can hear me, right? So welcome. So today I'm going to explain how we get from the Pokemons counted by humans. I assume you're all humans, right? And then we'll move to machines who actually can do it much faster in a data center, in a cluster. And I will show you the formalism, the logical walkthrough, and the physical implementation and all the details. Before I do that, I want to do a bit of a wrap-up of what we have been doing so far, because you know that we started with the first few weeks to look into the storage layer, because everything starts with storing data. When I gave you the Pokemons, the storage was the pieces of paper that were on my desk, and you all came to the front desk in order to get them, right? But when you do it in a cluster, it's not like that. The data is actually already all over the cluster. It's already there, and you directly read it from the machines. So in fact, the Pokemons, aka datasets, would be on HDFS or S3 or Hbase or your local file system if you want to do it on your laptop. But basically, there is a file system. Now, the good thing is that it can be any of those that we studied, right? Can be HDFS, S3, Hbase. It all works. This is fully orthogonal. So now, if we look closer, what do we have in here? Well, when I explain HDFS or S3, I just told you these are objects or files that are just sequences of bits, right? Then we saw a couple of weeks ago that these bits can be text. It could be, in fact, an XML file, a JSON lines file. So you know the data represented as text. So now if you want to train LLMs, that might be literally text, right? No particular syntax, but just, for example, here, the complete works of Arthur Conan Doyle. So Arthur Conan Doyle, which actually turns out to be public domain. So now I can actually, we can query that without any problem. And basically, you would have possibly text with billions of lines. So I don't think that Arthur Conan Doyle wrote billions of lines, but if you download the entire Wikipedia or the entire internet to the extent that you get, of course, the authorization, then you could have easily billions or trillions of lines of text like that, right? So this is something we could have. Or it could be text that is a bit organized. So you recognize here the CSV syntax, right? Comma-separated values. We could also have billions or trillions of lines like this. You might recognize the Zarcy-Lütte measurements. So this would be CSV, right? You recognize the syntax. But it could also be some syntax that is specific to what you are doing. In fact, I have in mind meteorology. So all the weather forecasts and the weather data, typically they don't use CSV. They don't even put the commas in there, but that has to do with the fact that the number of characters for every piece of data is fixed. There are always 4 digits for the year. The date is always on these many digits and so on. So then you don't even need the commas. You can just put it like this, but then it's on you to reconstruct the data, of course. But if it's fixed length, then you can do it without any problem, saves a bit of space. Then you could have a key value approach, meaning that it's like CSV, but with only 2 columns, and you can use a space, for example, as the separation. So here that would be mapping years to measures, right? You could also have JSON lines. As I told you, you have one JSON object per line. Technically, you could also have arrays and atomic values on a line, but generally it's really just object. I mean, as we discussed yesterday, right? So you see, in that case, you even see that it's heterogeneous. So JSON can do this. It could be binary, because if you listened to the lecture on the fact that if you validate JSON and the schema fulfills some properties, like not using whatever slots, but every type is correctly non-abstract, like integer, string, data, and so on, and you don't have any open object types, meaning that extra fields are forbidden, then if you have a collection of valid JSON objects, you can actually see it as a data frame, right? So I showed that to you yesterday, and I assume that now you have the visual of that. And the beautiful thing, if you have the data as a data frame in memory, is that suddenly it becomes massively faster, because it takes less footprint in memory, it's faster to compute, and it's all nicely organized by row and columns. So we love data frames. And we love them all the more that we like to store it back as a data frame on disk, and Parquet is one of these formats. So then on HDFS, you'd have a binary file that is actually Parquet and that has a data frame inside. But the benefit of doing that is, one, you have less to read because it's more compact. And second, it's organized by columns, so you only need to read the columns that you actually need to look at. So that can be binary. Now, another aspect of a data set, if you look at HDFS or if you look at S3, that's something I mentioned already a couple of weeks ago, is that typically a data set is not going to be in a single file. You could, right? But typically a data set is rather going to look more like a directory with plenty of files. And the data set is basically the sum of all the files. Typically, the files that you have in that directory have numbers like part 1, part 2, part 3, and these are called shards, right? Typically, we say that the data set is sharded, and every shard corresponds to one HDFS file. This is not to be confused with HDFS blocks, right? All of these files are HDFS files, so they are made of blocks, but these files could be a few gigabytes inside, right? Let's say 10 gigabytes, 100 gigabytes per file, so they would also be cut into blocks in HDFS, but the files are called shards, right? By the way, if you have a data set that is not sharded, and that actually sometimes happens, that you download, let's say, a gigantic terabyte file from the internet, there is a command line utility. I just forgot the name of it, but there is a command line utility that nicely shards it for you. So it takes the input and it outputs, let's say, 100 files, 100 times smaller. So it splits it into files, and then you can upload this to HDFS or S3. Why do we do this? Because you could ask, why don't we have just a single file with all the data? These are practical reasons, 2 reasons. The first reason is that I don't know if you ever tried to upload a 5 terabyte data set to S3 or HDFS, but what's going to happen is that you have, let's say, 1 chance in 2 or 2 chances in 3, that's right in the middle of it, because it's going to take maybe 1 hour, the network breaks and it interrupts the whole thing, and you have to start all over again and again and again and again until it maybe succeeds. It is very unpleasant, right? And you have to retry and retry and retry. So instead, if you use that utility to shard your file into plenty of smaller files, and then you upload the files individually to S3, then maybe if you upload 100, 98 will succeed and 2 will not, then you just try again with the 2 that didn't work, and that is quick, and that's much faster. Who understands that? Right? So this is really a practical reason. It's much easier to upload plenty of smaller files than a gigantic file to S3 or even HDFS. The second reason, as we will see, is that these data sets that you have, they can come from multiple sources. They could come directly, freshly from the CERN LHC device, right? Where you just collided the protons freshly, the hadrons, and then you collected the data. So that is more like a log. But some other data sets are actually the output of MapReduce or Spark, meaning that these are derived data sets that you obtained with a query. And if you look at the output of MapReduce or the output of Spark, it will typically be output in files like this, in many, many different files. Why? Because of parallelism. Because Spark and MapReduce are going to produce the output in parallel, and so it's more convenient that they write it as separate files in parallel. So this is the second reason why many data sets are sharded like this, right? For whom does that make sense? All right. So if you look at a data set, very likely it's going to look like this. Now, we saw that we have an alternative way of storing data, which is Hbase. Hbase can be seen as a 2-dimensional index on data, and here you can put whatever you want, including XML, JSON, but even binary files. You could even store Parquet files in Hbase if you want it, right? But XML and JSON would be maybe more common, or HTML. So it could also be on Hbase, right? That's also a possibility, and then we would just read Hbase instead of HDFS. So for example, we could have tables like this that might be in Hbase, right? That we have this data. Billions of rows, because Zurich has been going on already for 13 billion years. It could be like this, where we have Hbase rows where every row has an XML file, right? I didn't put the row ID. There would be obviously the row ID on the left. But basically, I assume that there is an XML document in every cell in here. I told you in Hbase, you can go all the way to 10 megabytes, right, per cell, if to be safe. You can go higher, but then it slows down. All right, and you see, as a nice recap of what we did yesterday, I even put the schema here that could correspond to all the XML elements that you put on Hbase. So this is one way of using schema validation and XML and Hbase jointly with one document per cell and the schema against which they are all valid. Okay? And then comes the hard-to-read querying that we are going to take care of today, right? That is the most interesting part. And what's going to happen is that we are going to do it in parallel, but this is a very natural thing to do because that data is already spread all over thousands of machines in a cluster. So doing it in parallel is actually a very natural thing to do. So one way to see it is this data is in the shards. You know, we just shred the data into these shards or even in HDFS blocks, and we nicely process everything in parallel. So now let's go to the querying side of things then. MapReduce was invented 20 years ago, roughly. The idea is that we wanted to kind of parallelize things, but we really, before, didn't really know how to do it, right? We just, you know how it is, right? You might have a piece of software that runs on your laptop, and you have multiple cores, and you would like to parallelize it. It's not really automatic, right? There is a bit of effort. Sometimes the compiler can figure a few things out, but it's not easy to parallelize, especially if you have an imperative language, right? That is a sequence of instructions, so you cannot really parallelize it so easily. But if you look at the algorithm from a declarative perspective and just imagine that this is my input, this is the output I would like to get, how can we come up with something in parallel? Well, you could do it on a case-by-case basis, meaning that use case by use case, you sit in a classroom in front of a blackboard and you just brainstorm on how to execute it in parallel. But what if we could have a generic way of doing that? Something very generic that you can apply to many, many different problems and at the same time simple. That is exactly what MapReduce is. So the idea is that this is, if you zoom out completely, you have some input data, you want to apply some query and you want to get output data, right? This is, you cannot do more generic than that. Now, we want some parallelism, so we assume I added these dash lines in here that basically says my input is partitions like this. In fact, that would correspond, as we will see, to HDFS blocks in here, typically 100 megabytes. And we want to output also in partitions like that. When we output, typically every partition gives you an HDFS file if you use HDFS, but I'll come back to that. But basically, we want some partitions here, and it would be nice if somehow in there can be some stuff in parallel that uses all the cluster. Now, if I make a wish list of what I would like to have, this would be perfect, right? If I manage to actually convert my query to just mapping every input partition to one output partition, this is perfect. I have basically 100% parallelized everything. And then you even get perfect improvements because if you have 100 machines, then it's 100 times faster. Who agrees with that? All right. But this is ideal. This is if in the ideal case that you can do that. That exists. You could think, for example, of a projection. You have a data set with JSON objects, and you want to remove a key in all the objects and project it. That you can do in parallel. You might have a filtering query. You want to select a subset of the JSON objects that fulfill a particular predicate. That you can also do in parallel, right? So I will come back to this. There are queries like that that work. But sometimes it doesn't. And you can think of, for example, sorting the data, or grouping the data, or aggregating the data. Then it doesn't work like this anymore. It doesn't work like something you can do in parallel. And the reason it doesn't is that you have this spaghetti because every output partition here might depend on many of the input partitions. So this is why you have this spaghetti here. And so the reality is somehow in between, that you have a bit of parallelism in there, and sometimes not, sometimes yes. But this is not very pleasant. So can we make it simpler and more generic? And in fact, when MapReduce was invented, it was noticed that some parts could be run in parallel, while some other parts might be spaghetti. And if you simplify that, this is what you get. You basically get this parallel followed by shuffle, followed by parallel, right? So the first parallel part is called mapping, and the second parallel part is called reducing. It is simple, and it is surprisingly generic. You wouldn't imagine the number of problems that you can solve with this pattern of parallelism. In fact, you can index the internet and index the web and build a Google like this. This is one of the ways you can do it. All right, so that's basically what we did with the Pokemons, right? So the map part was the first 8 volunteers that each had their batch of Pokemons that they counted. They produced key value pairs where the Pokemon was the key, the integer was the value. And then they shredded them. And then the shuffling was at the front where every mapper tried to communicate with every reducer to basically exchange the key value pairs. And the goal is that every reducer, so the 8 volunteers that reduced the data, had to gather all the Pokemon key value pairs that they were responsible for. And then the reducing was the sum of the counts. And then the output data was the 10 final key value pairs per Pokemon. Who is with me? Right? So this is the overall idea. Now, what is in there is called intermediate data. There is the input data, there is the intermediate data, all of these key value pairs that we threw away at the end that had the individual counts per mapper, and then there is the output data. If you look closer, these are all key value pairs. So for the Pokemons, it was very clear that the intermediate data was key value pairs and the output data was key value pairs, that you saw. For the input, it wasn't clear, right? Because these were just Pokemons on a piece of paper. But if you hit it with a hammer hard enough without hurting the Pokemon, you realize that you can also consider that the Pokemons are key value pairs. You just make up keys that are dummy keys that can be anything, and then the Pokemon has the value, and you just ignore the key, or the opposite. You can put the Pokemon as the key and an empty value, so you can turn it into a key value pair. So basically, this is the MapReduce paradigm that everything that you process is a key value pair. And so the input is a collection of key value pairs. The intermediate input is a collection of key value pairs. And the output is a collection of key value pairs. Everything is a collection of key value pairs. Okay. Now, the types can be different. You can have a type for the key and a type for the value for the input. You can have a type for the key and a type for the value for the intermediate output. And you can have a type for the key and a type for the value for the end output, right? They don't need to be the same. They can be different. In our case yesterday, these were Pokemons, and these were integers because we were counting them. And then you could imagine that this is whatever, and these were the Pokemons here. All right. Very often, I would say in 80% of the cases, but not always, you use the same key and value types for the intermediate values as for the output values. The reason is that the reduce function is typically just aggregating the values corresponding to a key. For example, it's computing the sum or the count or the mean or the max or the average of all the values that are associated with the type. So then it's convenient to just preserve the types because the key remains the same in the output. And the value type is the same because if you sum over numbers, you get a number. If you take the mean of numbers, you get a number. So this is why you also get the same value types at the end. Okay, it doesn't have to be though. That can also exist. Doesn't need to be, but in 80% of the cases, these are the same type. So now I'm going to drive you through the logical walkthrough of a MapReduce query. I insist on logical. This is data independence, right? As in every week, I'm first showing you the logical level, and then we'll get to the implementation, right? So on the logical level, what you do is you basically have this collection of input key values, and you have a map function that takes a key value, an input key value, and produces 0, 1, or more intermediate key values, right? So you have this map function. You're going to apply this map function to every single input key value. every one of them gets through the map function and might output 0, 1, or more key values. So the first key value output 3 intermediate key values. The second one output 0. Here you output just 1, and here you output 2, right? Can be any number. So this is the mapping phase. Then what happens is that you have all of these intermediate key values that were produced by the mapping phase. You just put them together, get a huge collection of intermediate key value, but just a huge mess. So what you do is you sort them logically, right? So you sort them so that all the key ones are together, all the key twos are together, all the key threes are together, and so on, right? So now it's nicely all sorted and grouped by intermediate key. And then you separate it by group. So all the key values, the intermediate key values with key 1 go together, all the intermediate key values with key 2 go together, and all the intermediate key values with key 3 go together. And millions of times, probably. Okay? So far, so good, right? And then you call the reduce function that takes a group of intermediate key value keys with all the same key, right? You only put all of those. It's basically both sound and complete. They must have the same key, and they must be everything that has the same key. They must all be here. That is the reason you can only do that when the mapping phase is fully finished. Otherwise, you saw what happened yesterday. The reducer had to do it all over again, or to basically update the results. So you need all. There is a question on Zoom, yes? Oh, maybe I can check if it's, oh, it's not switched on. Now it's switched on.
Yeah. To be clear, does this assume that the mapper transforms the values but keeps the keys the same?
Because of the incident with the sound, let me just read.
Okay.
That the mapper transforms the values. No, that's not implied. As you can see on the slide here, the keys can be completely different, right? You see, I'm using the Indo-Arabic numbers on the left, and I'm using the Roman numbers on the right. These need not be the same keys. This is fully generic. Does it answer your question? The first one?
Yes.
Yep, awesome. And the second one?
Question. So do all mappers reducers have to run the same function, or could there be a scenario where it would be beneficial for each to do something different?
No, there's just one map function and one reduce function. So in a MapReduce job, one map function, one reduce function, everywhere the same. But of course, if you take a different job, then you can change the functions. But within one job, it must be the same map function and the same reduce function. Okay? But of course, in the function, you can make it dependent on the key because that's any code, right? So it's Turing complete. You can do whatever you want in the function. Did that answer the question? Let's assume yes. Yeah, awesome. Okay, so we have, and then in the room, yes?
Oh, so before we saw using Hbase on top of HDFS, why was it preferable to have XML content in Hbase and tables?
Oh, I'm not saying it's preferable. You could also have XML in HDFS. All I'm saying is that I don't think people do it in the sense that when people use XML, they typically have one XML document per file and not one XML document per line. So I'm not aware of an XML lines standard, for example. And the thing is, when you have a lot of XML files with one XML document per file, you will have the problem that you have a huge number of files that are rather small. So if you have a huge number of files of 10 megabytes, that's not the sweet spot of using HDFS. So if you use HDFS, you like to have files that have a few blocks, right? For example, 1 gigabyte, 10 gigabyte files. But in Hbase, 10 megabytes is a good sweet spot, right? You can really easily process smaller values. So this is the reason. But you could also imagine introducing an XML lines format and working with XML lines. It's just that I don't think you will find data sets that give you XML lines on the internet as opposed to JSON lines. Right. Does it make sense?
Yes.
Yeah. So I'm basically saying it is possible, but that's just in practice what people actually do. Okay. All right. And so here you see that, going to the question on Zoom, the reduce function need not output keys that are the same. So here you have an example of a reduce function that has the group processing key 1. And you have in output key A, right? So it's generic enough to be able to do that. It can also output nothing, or it could output several keys, right? It's 0, 1, or more output keys per group of intermediate key values. For whom is that clear? How do they relate? Oh, you forget that then. You just have the output key values and you basically don't remember where they come from. Yeah, that was your question? Yeah, but there is a whole area of research called data provenance that actually worries about this, that tries to trace back every piece of data you get in the output to trace it back to the input, but that is orthogonal to this. Now, in the particular case that the intermediate key values have the same types as the output key values, then the reduce function looks like this. And then it's usual, it's not an obligation, but it's very typical that then the key is the same, right? So we have key A on the left and you also keep key A on the right. Doesn't have to be, but very often that's what you're going to have to be. And basically the value that you get on the right very often is obtained through an aggregation of the values here. Could be the sum, could be the count, could be the average, the mean, the max, the variance, or even something more complex, right? But you typically keep the key and aggregate this, right? 80% of the cases. But again, doesn't have to be. This is the most generic one. All right. And again, I insist, 0, 1, or more. You can have 0, you can have 1, you can have more than 1. This is totally fine too. It's generic. So you execute the reduce function in parallel. Yes, you have a question?
As far as I understood it, we map one key to one reduce process.
Exactly.
And if the map functions for some reason only output a set of a few keys, much less than we would have machines to execute reduce functions, could we still somehow layer this or distribute it over different reduce processes?
Mm-hmm. So you're already referring to the physical implementation, right? So here it's a logical walkthrough. Your question is already about the physical implementation. So just to make clear that this is a physical thing. Now to answer it, what happens, but we will see it, what happens is that if you have more reduce processes, we'll actually call them reduce slots, but process is just fine also to describe that. So if you have more keys, intermediate keys than reduce processes, then they are useless reduce processes. It means that some of the reduce processes will just do nothing, and then you will have one key per reduce process that was lucky enough to get a key. That's what happens. And it doesn't matter how large the groups are. You could absolutely have a million of key values in one of the reduce processes, and you could have just 2 key values in another reduce processes. Then what you get is basically an imbalance, right? You're going to have a hotspot in one of the machines that really processes a lot, and then in another machine is going to be a bit idle, right? That depends on your job and your map function and your reduce function. And this is part of the user's duty. If you want to come up with a MapReduce job and a map function and a reduce function, you have to think of these things. You have to think of how many intermediate key values would exist. Is it too little? Is it too much? Is it just the sweet spot? If it's too little or too much, then typically you try to rewrite your MapReduce algorithm in such a way that the number of intermediate key values is more suitable, right? So this is the idea. But this is highly dependent on the map function and the reduce function. So that's the first thing. The second thing is how physically you decide how many map slots you have and reduce slots, or map processes and reduce processes. So you have to make a decision also, and there are also heuristics for that. There is basically rules of thumbs that I will give to you to decide these things. Okay, did it answer your question?
Yes.
Yeah, all right. But it's great because you're always asking questions that are very relevant and that basically are already introducing the material that is to come. So this is perfect. It means that you are following and you're asking yourself the right questions. Okay. So yes, so the calls of the reduce function, of course, are done in parallel. In that case, with one output key value every time, but as I said, can be 0, 1, or more. And then we get this. So this is, if I zoom out, we had this input collection of key values that output via the map function intermediate key values. We sort them, that's the shuffling, right? We sort them all and separate them again by identical intermediate key. And then we call the reduce function on every one of these groups for every unique intermediate key. And then we spit out the output key values. In that case, 1 per group, but again, it doesn't have to. Okay, that's it. That's the logical walkthrough, right? Any questions on that? All good? Who is following for until now? Okay. So now comes the best part, because that's the physical implementation. How does that actually work in practice? How do you actually set it up in a data center? So now we look at the physical architecture. So first, as I said, it can work on HDFS, on S3, on Hbase, on Azure Blob Storage, on all kinds of file systems. It can even work on your laptop. You can run MapReduce on your laptop. It will still be useful because you remember that you might have cores on your laptop, 8 cores, 10 cores, 16 cores, and MapReduce will beautifully map it in parallel all over the cores, reading from your local file system. There is just one problem, is that the bottleneck is going to be your drive, because the drive can only read so and so many bits per second. So you will be hit, if you do it on your laptop, by the speed at which your drive is able to read the data, right? So just that as a warning. But on HDFS and S3, you don't have that problem because it's many, many drives that can do it nicely in parallel. Okay, so Hadoop MapReduce comes on top of that. So you can imagine that you have now thousands of nodes. We have a data center somewhere with thousands of nodes and terabytes or even petabytes of data. Even gigabytes can be fine. That can already be useful. Gigabytes, terabytes, petabytes of data. Now, what does the architecture look like? Well, this is easy. There will be no surprise because you already know this centralized architecture where we had the name node and the data nodes, right? As I said, these are processes running on machines, right? So we have the name node process and the data node processes. Then we saw that we have the HMaster process running on the same machine as the name node process. The region server processes running on the same machine as the data node process. And guess what? The same goes with MapReduce, at least version 1 of MapReduce. There was a new generation that I introduced later, but version 1 of MapReduce also had processes running on all of these machines. The one that runs on the coordination node is called a job tracker because it's for the entire MapReduce job, orchestrates the whole thing. And then you have the task tracker processes running on the same machines as the data node processes, and possibly, it doesn't have to be, but the region server processes. For whom is that clear? All right, so you see, we have this primary layer of storage, this optional secondary layer with which gives you low latency, and this third layer that is the processing layer. People often say this is storage and this is compute, right? Storage compute is a very short way of saying it, right? So, okay, so this is version 1 of MapReduce. For now, we'll stick to that version, and that's it. So the idea is that they are on the same machines. This is very important because that means we brought the query to the data. The data is already on HDFS in blocks. The blocks are already all over the cluster, already sitting on all the machines. And by running the map, executing the map functions on the same machines as the data already is, we don't need to move the data. That is the magic of it. We bring the query to the data. We bring the map function to the data. So typically what happens is that you might have your map function inside a Java jar, for example. The jar containing the code is uploaded to every one of the task tracker machines, and then they unpack that jar and take the map function inside and execute the map function directly on the same machine where the blocks are. Right. So what we need to add to the logical part, that's not a logical step, that's already a physical step, but what we actually do is that we split the input collection into sub-partitions of key values. So we don't actually have individual key values, but we have partitions of key values. We call them splits. And so what happens is that the map function is called per split several times. So it means that on that split that contains 2 key values. Of course, in practice, it's not going to be 2, it's going to be like thousands of key values, right? But you call the map function every time for every key value, then you produce all of these intermediate key values for every split. That's already a physical detail doing that. All right, so what happens is that if the data is already on HDFS, it is quite natural to say that a split corresponds to an HDFS block. So I'm going to look at split with a target size of 128 megabytes, right? And ideally, I take an HDFS block, all the key value pairs that are in that block give me one split. And then I call the map function on every one key value that is in that split, in that HDFS block. For whom is that clear? All right, so here I'm showing just one replica per block, but of course, you know, there's 3 replicas of every HDFS block. So now what happens is that the task tracker actually has processes, and more exactly threads, that are running on the machines. And every slot corresponds to a thread in the task tracker process. And we have map threads and reduce threads, map slots and reduce slots. And so what happens is that the map slots are going to be directly reading locally from the hard drive. You can short circuit, just like we did in HDFS. You can short circuit the whole thing and directly read from the local drive the key values that are in the splits that you want to process. Might not always be possible, then you can read remotely, right? It can happen, for example, that the yellow split would be processed by a map slot on a different machine. Then you just transfer the data over the wire. It can happen, you just want to not do it too often, because if you do it too often, it just slows down the job, right? But you can, right? It might not always be possible. It's only a goal. So what happens is that in the first phase, all of the map slots, so the threads, are active and invoke the map function over and over and over again in memory. And then at some point, the memory might become full. What do we do when it's full? The same thing as in Hbase. Remember, we flush it, exactly. So that's what you do typically if the task tracker memory is full, you flush it to the local disk, not HDFS, the local drive. You flush it to the local drive. You might even compact and so on, but that you already saw in Hbase, so I don't need to repeat. And you might compact as it is. So the same techniques we've seen in Hbase, except that then instead of H files, you basically have files that contain the key values nicely sorted. Is there a question?
Yes. Could you clarify again how MapReduce deals with the HDFS replication? How is it decided on which replica to map?
So the idea is that the job tracker is responsible for that. The job tracker is basically assigning the splits to the map slots. The way it's done, I will have plenty of animations that describe that in detail. So I'm already anticipating on what's to come. But the idea is that when you start, you pick a split on every machine and you give it to the map slots, right? And then you just keep in a queue the other splits. And as soon as the map slot is done, you take another split, ideally on the same machine, give it to it, and so on. At some point, towards the end, it might be that they are no longer on the same machines, and then you might need to read remotely, right? But this is something that happens dynamically, and this is done by the job tracker that orchestrates the whole thing and that has the overview of the splits. Does it make sense? To be clear, I'll come back to that. I have plenty of animations and slides to show you the details of that. We'll go into all the details. Yeah. Okay, awesome. Probably not today though, but probably next week. But I will give you all the details of that. All right, so this is what happens if the memory is full. Of course, if the memory is not full, you don't need to do it. Then you just keep it in memory, right? But you want to keep them sorted so that it's ready for the shuffling, right? So you do want to preserve the sorting. Then comes the shuffling. So for the shuffling, you need to send over the network wires, the intermediate key values, but they have to be at that point grouped by key, right? But since all the map slots kept the key values, the intermediate key values sorted by key, then it's straightforward to do, right? So what happens is that the reduce slots connect to every single map slots and request to download all the key value pairs that they need for which they have the responsibility. This can be done using hashes, using intervals. I mean, there are different ways you can do that. But basically, the reduce slots are assigned the responsibility for specific keys by the job tracker, and then they go and download from every map slots. That was the part where the Pokemons changed hands in the break. It would basically normally be the reduce people who request their Pokemons from the map people, typically. All right. Okay, so we have that, and this is over HTTP, that the intermediate key value pairs are shuffled all over the cluster. That's a bottleneck. That takes a bit of time to do that. So you probably want to design algorithms that try to keep it minimal, but you still need some amount of shuffling. Then comes the reducing part, and the reducing part is processing it all in memory, and then it writes back to HDFS. Typically, you are going to write one file for a reduced task, and typically in one file you have multiple keys, right, to not have two small files. But I'll come back to also. But basically, what you get at the end of that is that all the reduced slots wrote down plenty of files to HDFS called 1, 2, 3. Typically, they bear numbers in there inside the directory, and then you get what I told you, this sharded data set with plenty of let's say 1 gigabyte file, 1,000 of 1 gigabyte files. Okay, who is with me? All right, we are just scratching the surface here. I'm going to go more and more and more into the details to explain really everything of how that works. That is just an overview of MapReduce. Okay, still have 3 minutes. Maybe I can say a few words on input-output formats. So the input can technically be a lot of things, and the difficulty is that MapReduce expects key value pairs. And you know how the saying goes, right? If you have a hammer, then everything in the world looks like a nail, right? And so the goal here is that we need to make any input into a collection of key value pairs. But you know that not everything is a collection of key value pairs. So we need to turn tables to key value pairs, files to key value pairs, and so on. So that's the goal here. For tables, it's quite easy because the primary key kinds of give you the key and the other columns give you the value, right? So here it's pretty straightforward, right? For whom is that clear? Right, okay. So the row ID for Hbase would be the key, the rest would be the value and so on. So, okay, this is easy. Then for the files, you might have different formats. It might be text. You might have key value formats, for example, with a space between the key and the value on every line. And there are even binary formats that store key values, right? For example, sequence file. In fact, that's very similar. It's not exactly the same, but that's very similar to H files, because you already know that H files also store key values, sorted sequences of key values. So sequence files also store key values, and this is a format that is native to MapReduce to store the key values. So I'm probably not going to be much farther, but just to give you an idea of how you would turn text into key values, you basically break it line by line. So you use the line separator to separate the key values. You put the line, the actual characters in the value here. That's the value, the line. And what you put as the key would be the offset of the line. It means the number of characters from the beginning of the file. So for example, here there's 18 characters. So you use 18 as the key for this. Then you continue, you use 27 and so on. So you use the offset. For whom does that make sense? Right? So it's a bit made up because again, we hit it with a hammer hard enough to basically get key value pairs out of this. That's not the only way you can do it, but this is one of the ways. And then you have key value pairs. So now you can invoke a map function and so on, right? You're in the world of MapReduce. So before you go, I just want to make sure, of course, I have to click again, 29th, 30th already. All right. That's your opportunity to tell me slow down or accelerate. I had the feeling you were following though, right? When I asked, everybody's following. What does it look like? I think it's about right. We have a majority above 80%. Okay. So for those below 80%, again, I recommend, the first recommendation is read the textbook. I'm doing it with cats instead of Pokemons, but it works just nicely too. Ask questions to your friends and colleagues. There's no better way, by the way, to learn than teaching. So it's beneficial to both parties. Ask questions in the forum, solve the exercises, ask us, the TAs, also me, and we'll be happy to help, right? So especially if less than half, really ask around. There are hundreds of people who can help you. All right, so thank you very much, everybody. Enjoy the exercises, and I'll see you next week in E7 at 2 p.m. Thank you very much.